Historically, the bismuth phosphate process was originally used to extract plutonium from spent nuclear fuel. It was researched from 1943 to 1945 at the Oak Ridge National Laboratory. It was first used on a large scale at the Hanford site, Connecticut, in 1944, and then decommissioned in 1952 as it was replaced by the redox process. President Ford decided to suspend all forms of nuclear reprocessing in 1976 and 1977 in an effort to combat nuclear arms proliferation, as the fear of spent nuclear fuel being used to create nuclear arms was at an all-time high. President Reagan lifted Ford's ban in 1981, but did not provide funding for any nuclear reprocessing programs, and thus essentially changed nothing concerning nuclear reprocessing. The timetable and procedure for establishing a permanent and underground repository for high-level waste was created with the Nuclear Waste Policy Act of 1982. Yucca Mountain, Nevada was designated for study in 1987. Yucca Mountain was then approved as a site for high-level waste storage in 2002 by President Bush, but in 2010, President Obama eliminated all federal funding for the project. The Blue Ribbon Committee was then established by President Obama to provide recommendations, but the future of waste storage remains uncertain.
When most people think of green energy, they probably think of this, or this. But America's biggest source of green energy, by far, is this. Today, there are 104 nuclear reactors in 31 states, producing more than 800 billion kilowatts of electricity each year, without emitting greenhouse gases. Those nuclear reactors run on uranium. A single uranium fuel pellet less than an inch long generates about as much energy as 3 42-gallon barrels of oil, or 1 ton of coal.
Reprocessing used fuel to recover uranium as reprocessed uranium and plutonium avoids the wastage of a valuable resource. Most of it, about 95%, is uranium, of which less than 1% is the fissile U-235, and up to 1% is plutonium. Both can be recycled as fresh fuel, saving up to 30% of the natural uranium otherwise required. These materials, potentially available for recycling, could conceivably run the U.S. reactor fleet for about 30 years with no new uranium input. The main form of nuclear reprocessing fuel is through the use of Purex. This involves dissolving used fuel elements in concentrated nitric acid. Chemical separation of uranium and plutonium is then undertaken by solvent extraction steps. The first step, the used fuel is chopped up and dissolved in hot, concentrated nitric acid. The second stage separates the uranium and plutonium in the aqueous nitric acid stream from the fission products and minor actinides by a countercurrent solvent extraction process using tributyl phosphate dissolved in kerosene or docaine. In a pulsed column, uranium and plutonium enter the organic phase while the fission products and other elements remain in the aqueous raffinate. In the second pulse column, uranium is separated from plutonium by reduction with excess U4+ to the aqueous solution. Plutonium is then transferred to the aqueous phase, while the mixture of U4+ and U6+ remains in the organic phase. It's then stripped from the organic solvent with dilute nitric acid. The plutonium nitrate is concentrated by evaporation and then subject to an oxalate precipitation process, followed by calcination to produce PuO2 in powder form. The uranium nitrate is concentrated by evaporation and calcined to produce UO3 in powder form. It's then converted to UO2 product by reduction in hydrogen. The plutonium and uranium can be returned to the input side of the fuel cycle, the uranium to the conversion plant prior to re-enrichment, and the plutonium straight to MOX fuel fabrication.
Conceptually, reprocessing can take several courses, separating certain elements from the remainder, which become high-level waste. Reprocessing options include those seen below. In today's reactors, reprocessed uranium needs to be enriched, whereas plutonium goes straight to mixed oxide, or more commonly referred to as MOX, fuel fabrication. For certain reprocessing needs, a number of Purex derivatives have been developed. A modified version of the Purex that does not involve the isolation of plutonium stream is the Urex process. This process can be supplemented to recover the fission product iodine by volatilization and technetium by electrolysis. Another modified version, CoX, allows for the co-extraction of both uranium and plutonium. This process is currently in the development phase, but is nearly ready for industrial use. If put to use, this process would create a product containing 20 to 80% uranium and would make MOX fuel for light water and fast reactors.
Pyroprocessing is a process that takes nuclear waste and separates uranium, transuranic elements, and other fission products so that they can be reused again as fuel in a second reactor. If pyroprocessing can be correctly utilized, it will offer a thorough fuel cycle between LWR reactor waste and fast reactor fuel. Like other nuclear processes, pyroprocessing isn't considered to be totally clean, though the waste is well managed. Waste minimization is achieved by using electrochemical processes to remove fission products before the electrorefining of the fuel. Additionally, collecting the bulk of the fission products as metals and producing tailored waste forms also reduces the amount of process waste. The metal waste can't be easily reduced, but there are strong possibilities for minimizing the ceramic waste. Some of the fission products that generate high levels of heat, like cesium and strontium, can be separated to form other fission products that can more easily and safely be placed into short-term shallow disposal. The remaining metal fission products can be concentrated into a ceramic waste form by using an ion exchange process. This process has been estimated to reduce ceramic high-level waste by as much as a factor of 3 relative to the widely used throwaway process. The pros of pyroprocessing highly outweigh the downsides. By using this method of waste treatment, a much higher percentage of overall fuel is used. It's also a cheaper process than Purex. Pyroprocessing also simplifies high-level waste into a more readily disposable low-level waste. As of today, 2 separate pyrochemical processes have been identified, but they are yet to be feasible from an engineering standpoint. Though if it were to be successful, pyroprocessing could greatly improve the nuclear waste cycle.
The process of separating the useful stuff from the trash is called pyroprocessing, a nifty technology invented by Argonne scientists. Pyroprocessing uses electrical currents and chemical reactions to separate the useful materials from the waste. The main part of this recycle process is being tested here.
This is a large argon inert atmosphere glove box. It allows us to work with uranium metal and large pieces of electrorefining equipment to test operations efficiency.
After chopping the fuel rods into small pieces, you submerge them in a vat of molten salts. When you run an electric current through the vat, the uranium and transuranics separate out and forms crystals on the electrodes. Then we form new rods out of the newly recycled fuel and put them into a fast spectrum reactor, which is an advanced reactor that lets us capture the enormous amount of energy that's still contained within the rods. If we recycle this way, we could power the US for thousands of years, using just the uranium we've already mined. The leftover fission products can be converted into a stable glass form to be safely stored underground.
This is aluminosilicate and glass. It's a very durable waste form. So this then would be loaded into waste containers and placed in a repository.
In that repository, the glass only needs to be stored for 500 years, which is much less than the hundreds of thousands of years for untreated fuel. Replicate and repeat as needed, and you have nuclear reprocessing.
In terms of economics, nuclear waste reprocessing is many times more expensive than storing it, although reprocessing allows time for nuclear decay time to decrease. Countries such as France engage in these nuclear reprocessing activities, and other countries such as Japan ship spent nuclear fuel to places like France for nuclear reprocessing. Reprocessing provides vast economic benefits in the long run, but current initial investment required is too high to attract potential investors.